Hello everyone, I'm Vincenzo Porrino from the University of Naples Federico II, and I'm glad to be here to present you the SCORE project, a mission for the exploration of a long-period comet through a flyby. But why do we want to explore long-period comets? Well, long-period comets are celestial bodies with a very high orbital period that is greater than 200 years. Because of this, they have never been contaminated by the different passages in the inner solar system. Because of this, they have never been explored by previous missions, but in the past there were only some missions that were planned but never became reality, such as the LOCO mission. They can bring new important scientific results regarding the origin and the evolution of the solar system and of the life on Earth. In addition, deep space exploration missions with microsatellites are not so common, thus SCORE can be an important test bench for new technologies and subsystems. For example, it makes use of electrical propulsion, and in particular it makes use of the HT400 electric thruster, which is an innovative technology that can increase the maximum distances reachable by microsatellites without increasing too much the weight, due to the high specific impulse of the thruster that can be up to almost 2000 seconds. Another important technology is the shielding against the micrometeoroids that combines already existing materials in a new configuration, providing a reliable protection with a limited mass. This technology and these materials, which are Kevlar and aluminium, can be really helpful also for other missions and not only cometary ones, since the shielding against micrometeoroids are really important also for low Earth orbit environments in which there are a lot of debris on the orbit. Let's now see the main scientific mission objectives. Well, we can see here that the mission objectives are determining the nucleus characteristics of the comet, determining the coma composition, and determining the morphology of the comet. That means determining the size and the shape. We do this with the payloads listed in this slide, and in particular we can see that we have a thermal camera, an infrared spectrometer and a multispectral camera as optical payloads. In addition to the optical payloads, we have a flux gate magnetometer to measure the magnetic field of the comet, an impact sensor to measure the momentum of the impacting cometary grains in order to evaluate with a higher accuracy the cometary dust environment, and then we have a mass spectrometer to measure the ion composition of the coma. But one of the main difficulties is that the target is uncertain, and it can be discovered only a few years prior to its passage at the perihelion. Because of this, we need backup targets to guarantee a meaningful scientific return of the mission, and the backup targets have been carefully chosen in the following list of short-period comets. In the table we can see, other than the orbital parameters, also the flyby date, which is the date of the next occasion to perform a flyby with that comet. And in the last column we can also see the last encounter with that comet. Let's now take a look to the different mission phases that characterize this mission. First of all, SCORE will be deployed during 2029 on a cislunar L2 southern near rectilinear halo orbit by another mission, such as the Lunar Gateway. The spacecraft will wait on the parking orbit until a suitable target is detected. The target to be suitable shall intersect the ecliptic plane in the region of space in between 1 and 1.58 AU from the Sun. The lifetime of the mission shall not exceed 6 years, and, as we will see in the next slides more in detail when we will talk about the single mission phases, the duration of the single phases will depend highly on the specific target. Here we can see the lunar parking orbit, which has a perihelion radius of about 16,000 kilometers and a period of about 10 days. This orbit is stable for more than 1000 days without station-keeping maneuvers. Because of this, as we will see later, it is not sure that we will need station-keeping maneuvers, because the maximum waiting time set by requirement on this orbit is of about 2 years and not 3 years. This means that only in the case that we will have to wait for a backup target, station-keeping maneuvers will be needed, and if needed, their magnitude will be very low, of about 1 meter per second per year. Eclipses instead occur every 1 or 2 lunar synodic period, and their duration is really short, of about 160 minutes. A probabilistic analysis has been made in order to evaluate the orbital parameters of a generic long-period comet and to evaluate the maximum time the satellite shall wait on the parking orbit. This maximum time has been set as the maximum time between two subsequent discoveries, which is 2.1 years. This value has been obtained by the average time between two discoveries plus 2 times the standard deviation, values that have been obtained through the probabilistic analysis. Once a suitable target is detected, the spacecraft shall depart from the Moon and the Earth's sphere of influences in order to start the interplanetary transfer. This departure is made with chemical propulsion in order to win the gravitational attraction of the two bodies. There is a possibility to start this maneuver once every 29.5 days. We can see also that the delta V to leave the Moon or sphere of influence is low due to the fact that the parking orbit has an high perihelion radius. Then, once we left the Earth's sphere of influence, we can start the interplanetary transfer, which is performed through electrical propulsion. Two strategies have been proposed, a single finite burn and a double finite burn. The single finite burn is cheaper and takes less time than the double finite burn, but it doesn't cover all the regions of study. Thus, depending on the particular mission scenario, one strategy may be preferable to the other. Once we reach the comet, we will start acquiring the data. The quantity of the data will depend on the relative velocity between the satellite and the comet. We evaluated the relative velocity through the probabilistic analysis before mentioned. Instead, the quality of the data will depend on the closest approach distance of the comet, which has been set nominally to 600 km. This distance depends on the attitude pointing requirements in order to survive the impacts of particles of 100 mg. This only if one reaction wheel fails. Instead, if we reach the comet with all the reaction wheels working, we can also decrease the closest approach. We can do this because the chosen reaction wheels provide 1 Newton per meter per second angular momentum, and, as we can see from the figure, while the orange curve refers to the case of one wheel failure and we exceed that angular momentum limit at about 600 km, in the case all the 4 reaction wheels are working, we refer to the blue curve that reaches the limit of 1 Newton per meter per second at about 250 km. The study of the cometary environment has been really important to develop a suitable shield that protects the spacecraft during the flyby. In particular, the designed double Whipple shield ensures the protection against 100 mg particles up to flyby velocities of 64 km per second. In these figures, we can see the probability of encountering critical particles in function of the closest approach distance. As we can see, if 100 mg particles are not critical, we have always a risk of destroying the spacecraft lower to the 2%. Instead, if these particles are critical, so if the flyby velocity is higher than 64 km per second, the risk reaches the 2% at about 340 km from the comet. In this latter case, we are not interested in the attitude pointing requirements, since a particle of this magnitude will directly destroy the spacecraft without instabilizing this. Once the data has been acquired, they have to be transmitted on ground. The data transmission time is 8 hours a day, and the duration of the transmission will highly depend on the previous phase. For example, a simulation has been performed in the worst case. In this case, we consider the maximum duration of the parking phase lasting 2.1 years, which is equal to the maximum waiting time, and the transfer phase lasting 2.6 years, that is equal to the double finite burn duration. In this case, the remaining duration of the mission, to reach 6 years of total lifetime, will be the difference between the total lifetime and these two values. This leaves us with only 1.3 years to dedicate with the post-flyby duration. In this worst case, we have a maximum of 30 GB of data transferable. But this value is only the worst case, and depending on the particular mission scenario, it will increase. In the post-flyby phase, the scientific data are transmitted via an X-band high-gain antenna. Instead, during the parking phase, telemetry and command are transmitted through an X-band low-gain antenna. In addition, the high-gain antenna has a proper mechanisms in order to be protected from the cometary dusts and the thruster plumes. Let's now take a look to the space segment description. Here we can see the mass budget, the power budget, and the link budget. In addition, we also reported the power subsystem characteristics. In particular, solar arrays have been sized according to the transfer phase, which is the most power-consuming phase due to the electric thrusters. In the mass budget and the power budget, we can see the some margins that have been chosen accordingly to the AIA regulations. These margins refer to the phases 0A of a space mission to which this study extends. Costs have been estimated by simple cost models given by NASA, resulting in an average value equal to $35 million. We want to underline that this value is only a rough estimation of the cost, and through a more accurate cost analysis, the budget is expected to reduce. In addition, since the mission may be a module of the Lunar Gateway, its funding can be connected to the Artemis program, for which deep space missions deployed directly from the space stations may be planned in the future. A risk analysis has been performed throughout the project, supporting the design phases. Different root causes have been defined, each one of them with their impact and likelihood. From these root causes, a fever chart has been made. A reliability analysis has been performed with Weibull distributions. Two analyses have been made. The first analysis considers a specific mission scenario in which only the most stressed subsystems are considered active in each phase. The second analysis is a worst case, in which all the subsystems are always considered active. In this way, we evaluated the reliability range in between 86 and 90%. In conclusion, this study demonstrates the feasibility of the mission in terms of risk, mass and size constraints. It also demonstrates that it is possible to design a scientific interplanetary mission with microsatellites. Obviously, there are some critical aspects of the mission. One is the electric thruster, which should be carefully monitored during its development. This technology is the key technology of the mission, because it's important to develop it up to an acceptable TRL during the design phases. Another one is the fact that the target will be known only once the satellite is on orbit. Hopefully, this mission will be a solid starting point for the development of new interplanetary missions with microsatellites. From my side, this is all, and on behalf of the SCORE team, thank you for your attention.